All right, morning, y'all.
Morning.
Everyone grab sheet, if you haven't already. Yeah, 2 right there.
Are we gonna go over the final or
That will be Friday.
Friday?
Yeah. And there will be an email announcement for the written version of what will go over Friday, forthcoming.
This Friday or next Friday?
No, this Friday, the final is next week.
Next week. Okay.
Yeah, the
That's
final
what
is
I
next
said.
week.
Okay.
And I remember hearing there's like a standardized chemistry test that we're taking.
Yeah, that's the one.
Okay.
Yeah, so there's a lot of anxiety that happens from that as a result. So basically, what the Friday lecture will be and my email will be, I'd say half of that will be just me kind of lowering the anxiety, basically just telling you this is what's going to be there. Don't worry about what you can't do. I'm only going to grade what we have covered. And there's a massive curve, and then get the anxiety down. So that's the next. That's
Will there
Friday
be
in a
a
nutshell.
study guide or some kind of like study material that?
There will be some things I'll mention in email. There is a practice final that I put on active. If you go to the practice section
And that'll be all the
of
stuff.
active, it's not gonna be the same questions because I don't write the final, but it's going to be similar. It's just comprehensive.
Okay.
Yeah. I mean, I guess we could talk final today and then do nuclear Friday, but that's maybe what people are wanting. Make sure I get the right camera. All right, yeah, I guess I would be okay doing that. That's kind of at the top of people's minds. I don't know if I'll spend like the whole day today going over the final, but just at least some brief comments to get people in the right direction. And then we'll do our last topic for the semester, good old nuclear chemistry. Okay. So I'm going to send an email to this effect, but basically here's the final in a nutshell. Okay, where are we gonna do it? It's gonna be right here in this room, same time as class. It was this Wednesday at 11. Okay. For those in my like online section, some of them may join us in here. Others, I'm gonna have different like appointment times with them. So there's a few like random people on Wednesday. They're from my online sections. All right. So you got 55 minutes. It is timed, and I know some of you have time and a half or 2 times allowances. You would get that time adjustment. But for the rest of us, it's 55 minutes for 60 questions. And that sounds a little scary on a breakneck pace. I don't write it. It's written by the ACS Exams Institute. Okay, American Chemical Society. Okay. We give a standardized final for a variety of reasons. We are a transfer institution, so many of you have to make sure your Chem 101 class transfers elsewhere. And so this is a way of benchmarking your performance on a national scale. We grade it in 3 ways, okay? 3 grading methods. And I'll send a chart with all the numbers and stuff, but there's going to be raw score, which is just your usual grading. So like if you got, a 54 out of 60, that's a 90%. That'd be your raw score, okay? And then there's a percentile ranking. And that's how you rank nationally speaking. All right, and so you can go anywhere, no one's gonna get 0, but there's 0, 1, 2, 3, da 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 da, 90, da da da, 100. Okay. And since it is a timed exam and sometimes people don't get everything done or know everything and it's not written, the rankings are pretty generous. Let me show you an example. There's one year where a 40 out of 60, that's a D, that's a 67% in a raw score, but you would have been a top 10% in the country. Okay. And so that percentile ranking would be at 90%. And so if your percentile ranking is higher than your raw score, and often that will be the case, you will just get the percentile instead. Okay. And then the last way we grade is, I'll just call this the curve. We do a statistical analysis, statistics, okay, and we do a bell curve, okay. And before you think this will hurt you, this helps you. So let's say the average score, was like a 30 out of 60, okay. And I know, and this happens. Okay, because these tests are not designed to be graded on a letter scale. It's designed to be for this more. We don't find that fair. So at CSI, we went one step further. And we said, hey, if that's an average performance nationally, then that's a 75% C. Okay. And then if you're like about a standard deviation out, we call that, 85%, and 85%, that may have been only like, a 40 or a 45 out of 60 or something. And so even if you have failed it from a number point of view, you actually got a C. So basically, what often happens on the exam is people, they'll first look at their raw score, be like, oh crap, I killed it. I got killed, and I didn't kill it. I got killed. Okay. But you'll see the way I have it programmed in Canvas, I drop the lowest 2 of these methods and you keep the highest, and you'll often see that your performance on the final is equal to or often even better than what you've been averaging on my exams throughout the semester. Okay. So it's not going to feel generous in a moment. Once you're done with the exam, you're going to give me the stink eye. You're going to be like, really, Josh, you end this semester like effing up everything. Okay. You're going to walk out here angry, and then you'll see your grade. You're like, oh, okay. That wasn't half bad. So yeah, that's basically the gist of it. Friday, I'm going to get more to details of the review of the topics and study tips. And I'm going to spend a lot of time reviewing the blind spots that people forget throughout the course. I don't know what that's about. The blind spots that people forget throughout the semester.
I think it's one of the cameras disconnected.
Yeah, probably. Okay. For example, like there's a time period like we would get empirical and molecular formula from molar mass data. Like a lot of us, we knew how to do that pretty well, but I'd say most of us at this moment, if I asked you here's some data, I'd say half of us, even if we knew how to do it, would have forgotten how to do it. So a lot of Friday will be getting those quick refreshers, kind of just back up the speed, because most of this exam, as you can see from the mathematics of it, you have less than a minute per question, but you'll see a lot of questions, and a lot of them will indeed take less than a minute. It's going to be stuff like, hey, how many valence electrons in the carbon? You're like, well, that's 4. And then you put the 4, that took 10 seconds. You spend more time doing the bubble than thinking about it for a lot of those questions.
Is it multiple choice?
Yeah, it's all multiple choice. Yeah, everything has, everything's multiple choice. Everything's multiple choice. Yeah. So like you'll see on the active practice section, most of what I put there was either multiple choice or just really fast stuff. So it's like fast. And like, I'm not saying it's not in depth, but a lot of it isn't in depth. But a lot of it is like, you either know it or you don't. Okay. And so again, one thing we'll talk about Friday, but I'll just put in your head right now, is you'll just kind of go through the exam, do all your fast ones, and then you kind of just make markers of like, oh, number 7, that looks like it'll take a while, or I hate the way it looks, so I'll go back to it later, and you have your little list. It's gonna be very strategic, okay? But yeah, it's like for someone who's like been in the game all semester, which has been all of you, like a lot of it will be more familiar than you believe. So my biggest study tip for the final is make sure you studied up for the exam for this week because that is indeed some of the material. Okay, so get that over with first. First things first, and then we'll enter the plow of anxiety on Friday. Okay, and on top of this, I don't speak for all Chem 101 instructors, but this is my own personal policy. Any material on the final that I didn't get to in my class this semester, I'm not going to count it against you. So I don't know if mathematically that it's effectively bonus or not. No, I think it just gets removed from the calculation. So it's not bonus, it just gets removed from the calculation, and then I adjust accordingly. So you won't be penalized on that. And some semesters, like when I'm not like taking a new online class on the side, like there's maybe only 3 to 5 questions that you had never seen before. This semester, I'm gonna be honest, it could be like 15 of them, Don't worry about them. I know what they are. I'm not going to grade them. Okay, it won't hurt you. So basically, with the material remaining that I have covered, it's like a final that I kind of wrote in that sense because it's stuff we covered. Peter,
There's a practice, right?
there's a practice on active right now.
Okay, so, will there be the ones that we haven't seen yet on the practice or no?
I don't think there's too many of those. No. Let me know if there's like, Josh, this is really left field. And a good chance if you've never seen it before, then yeah, it's not going to be like something I mark against it. Fine. Yeah. All right. Hopefully that was the little taste you needed for now. And then Friday will be more dedicated. I have all that time spent for like, it's our cleanup lecture. Okay. Okay, good stuff. All right, so anything else? Anything else? All right, good. So again, Wednesday at 11, I'll tell you more on Friday in the email, but basically come here like 10, 15 minutes early, just to get the good vibes going, make sure you had time to go to the bathroom, eat a snack, all that stuff. Okay. I also use that time to clear calculators and stuff so that we can start, on time and not hold up the boat. Okay. All right. So let's get into nuclear chemistry then, if there's nothing else. All right. So if you just walked in, make sure, yeah, I'll do you a solid. Anyone else? Let's walk in. All right. All right. So if you're online, then you'll need to go to Canvas. You'll need to go to Canvas to find the handout. All right. So it's at the top of our course page. Okay. All right. I see 2 of you online. Okay, there may be others watching this recording later. So I'll look in the chat to see, I'll give you all a minute, see if you're able to find the nuclear chemistry worksheet. Okay, both of you found it. Awesome, awesome. All right, very good. Okay, so there's 3 pages to the worksheet. All right, page number 1, I kind of called it the ABCs of nuclear chemistry from A to Z. All these little puns are intended, okay? We'll go over a bunch of different types of nuclear reactions. I did forget one on the front. let's see. Electron capture. So we'll go over all these different types of nuclear reactions, okay? And then on the back, you will see something about half-lives, okay, nuclear decay. So this is like how much material is remaining in its original form after you've had these half-lives. And so we'll do a half-life example. Okay. But this is where we're going to start our little journey. Okay. This is called the chart of the nuclides. The chart of the nuclides. Okay. I printed this from Brookhaven National Lab, okay, out in New York. All right, so before we just start pumping out a bunch of random nuclear reactions, I think it's important to spend some time in the why, okay? The why of why nuclear reactions even happen in the first place, okay? And so this is what you need to know for today. If you have a stable nucleus, it's not going to be radioactive. But therefore, you're going to need an unstable nucleus. And that will be radioactive. Okay. We have to get our nucleus to be unstable, or find a nucleus that is unstable. Okay. So the focus of today is going to be nuclear instability. Okay. And when you have a nucleus that is not stable, and when you have a nucleus that's not stable, that atom will change itself in order to become stable. Okay. Everything we've talked about up until this point of the semester has been stable. Okay. And what do we mean by stable? Okay. Well, to figure out what stability means, we have to go to the science. Okay. So on this printout, everything that is a black square represents a stable isotope. Okay. And then anything with color is going to be unstable. Okay. And the way they did this chart is like dark blue means like somewhat stable, but still unstable. Okay. Somewhat stable compared to other isotope, and then like the lighter greens or lighter blues, lighter greens, and then the yellows. And like by the time you get the yellow, it's very unstable. Unstable means it's not going to exist for very long, okay, before it decays. All right, now we can think of stability as a time thing, okay? If it's stable, it exists for, well, it exists for infinity years. It exists forever. Okay. If you're unstable, we're going to measure how long you exist in terms of a quantity called half-life. And some people hyphenate half-life. Some people write it as a HL. Some people write it as a T with a subscript of a half. Okay. And a half-life is the time it takes, time for half of material to transform. Okay. To undergo a nuclear reaction.
Half-life is also used for like prescription stuff.
There's biological half-life, yeah. So how long something is in the body before something happens. Okay, so how long it takes for half of whatever was put in your body for it to be excreted, or metabolized, that's biological half-life. So they'll talk about that in like pharmaceutical contexts often. Okay. Yeah, whereas in biology though, like if it's metabolized, that means you have chemically altered like the drug. But if it's excreted, then you didn't necessarily transform it, you just got rid of it. Okay. All right, but here we are talking about transformations. Okay, we're going to talk a lot like uranium today. Okay, uranium, when it decays, it transforms into thorium. It didn't poof disappear. It just transformed into something else. Okay. So how long it takes before transformation happens. And just to keep the mathematics simple, we measure in halves. Okay. Because as we'll talk about today, okay, you never lose everything. I mean, 10 half-lives out, a lot of people consider it like 0. Okay. But it's like 0.1% actually. Okay. Take a long time to get rid of everything. And the half-life of uranium, like 238, is like 10 million years. Okay. No, 5 billion years, excuse me, 4.5 billion. But anyways, it's a long time. That means for all your uranium to go away, well, for half of it to go away, it'd take 4.5 billion years. For half of the next half to go away, it'd take another 4.5 billion. Okay, so it's going to be around a while. Okay. All right, but here's the stability piece. And here's the stability piece. Okay. So we got all this black here. Okay. Our stability is like that. Okay. I want to show you something. This I think is super cool. Okay. I want you to notice as you go on the periodic table, on the most part, the number of protons and the number of neutrons are often equal to each other. Not all the time, but usually. Check this out. Okay. Well, hydrogen doesn't have any neutrons on the most part, so I'll skip, but we'll go to helium. Atomic mass number 4. 2 protons, 2 neutrons. 4 minus 2 is 2. Okay. For odd numbers, that's not possible, right? But you go to like carbon 12, 6 and 6. Protons, neutrons. Nitrogen, 7 and 7, 8 and 8 for oxygen. 9 and 10 for fluorine, a little bit more neutrons, but whatever, we have an odd number. Neon goes 10 and 10. This trend mostly continues until calcium. If you look at calcium, average atomic mass of 40, that means about 20 neutrons per calcium. Okay. And then we got scandalous scandium added again. Check this out. Okay. 21 versus 23. Okay, we have a break of 45. We have a break of like 4, 3.5, 4. Okay. And it never ever stays the same again. You'll see that scandium onwards, you have more neutrons in your nucleus compared to your protons. All right. So you can draw a line on this page for effect. I'm going to cheat because I have a ruler. Okay. All right. So right there is 20 and 20. We can draw a line. And this line is the Z equals N line. And Z, of course, is another letter for protons. It's when our protons and our neutrons are equal to each other. You'll notice for most of the periodic table, it doesn't hold true. I love that. It's so interesting. Okay. All right, we got the neutron side, we got the proton side. So for most of the periodic table, what do you got more of? Neutrons. Okay. So let's think about it. In your nucleus, you got protons and neutrons, yeah? Okay. And one thing we know about protons is, well, they have the same charge, so they're going to repel each other. Okay. So way back in the beginning of the semester, we talked about the like 4 fundamental forces, and we talked about like strong nuclear force, and then you had electromagnetic force, which is just plus and minus charges. Okay, so I'll just call it the charge force. So you had strong nuclear force, then you had the charge. Then you had gravity, and like gravity is like, you know, the charge force is like thousands of times weaker than a nuclear force. And then gravity is like 1,000,000 times weaker. Okay. So we got strong nuclear force going on, holding the nucleus together. Okay. And that is what's preventing the pluses from repelling each other. Okay. But everything has its limits. You have too much pluses in the nucleus, too much repulsion, and that nucleus has to change. Okay. It's warm in here, ain't it? I'm gonna crack, yeah. Everyone's eyelids. Yeah, let me. If anyone needs a Monster, I'll just give you my credit card. You can get a Monster. Okay. All right. She never came back. He never came back. Okay. Anyways, so yeah, you need more neutrons, right, to buff things out. Okay, but there's a dilemma here. Neutrons are spacers, but neutrons provide less strong nuclear force. Okay. So you can't overload the neutrons either to a certain extent. Okay. So the long story short is there's a sweet spot. The sweet spot for most of the periodic table is a little bit more neutrons, but don't overdo it either. Okay, so the black, that is our Goldilocks. Okay, and anything below it, it's got too many neutrons. And then this other side got too many protons. Okay. And when there's instability, nature works to correct the instability. So how are the nuclear reactions going to go? If you got stuff with too many neutrons, it's going to get rid of them. Okay. Everything wants to go to the center black. Okay. Build your home inland, not on the shore. Okay. If you got too many protons, things are going to go that way. Okay. You're going to get rid of the protons. Okay. That is a story of nuclear chemistry. Okay. If you got an unstable atom, it's going to transform itself. We're going to change protons or neutrons in order to get stable. Okay. This is not something we encounter in everyday life. In everyday life, we only deal with the black squares. Okay. It's only if you work in astronomy or in radiochemistry, nuclear physics, you know, as a uranium chemist, that's where you start working with the weird stuff. Okay. You either need to be in a star or a nuclear reactor to start making these sorts of things.
There's no like natural occurring radioactive.
Not many. Yeah. So great question. There's a term for naturally occurring radioactive materials, norm. Okay. And norm principally consists of uranium and thorium. Okay. That's because uranium and thorium, they have very long half-lives for a radioactive material. We're talking billions of years. And so you can find them on Earth. Okay. Yeah, this is to talk about natural abundances, it starts having implications of like how long, you know, from a scientific perspective, like Earth has been around and stuff like that. And so to be clear, I am not endorsing, you know, any sort of opinion of how we got here and stuff like that. I don't want to lose my job, right? Okay. But when scientists try to come up with a scientific date for the Earth, they will look at what radioactive materials are around. And so you got thorium and uranium, they got half-lives on the order of billions of years. And so when you look for other radioactive materials, you don't find them. And so that's how people think of like, oh, maybe that's the date for the Earth or Milky Way or whatever, because we don't see these shorter nuclides, okay? But maybe at the beginning of Earth, maybe they existed when stars were smashed together and stuff like that because, well, Earth was young at that point. Okay.
Okay.
Yeah.
So like
Yeah.
they're in the form of it like because of like the crazy temperatures and like
Yeah.
it formed and then because it lasts so long, it's still there. So they're how do they like know like the actual like date of uranium or like
Oh, it's through mathematics. So glad you asked. So you make a trend line basically. If you have like pitch blend, I'm talking I have a there's a science teacher at O'Leary Middle School. He's wanted to give me his old uranium sample, so I'm stoked about that. So you get some uranium, okay, and you'll see how its activity changes over time, okay, and you'll see like at this very moment you have 1 billion disintegrations per second or whatever, and then you measure like a year later and it's like a little bit less and a little bit less, and as the activity changes, you apply something called an exponential trend line. And when you apply that exponential trend line, let me get a clean sheet. Remember like when we did the Penny lab, like we had that exponential trend line? Depending on the radioactive material, you're gonna have a different decay. Like something that's super hot, decays crazy fast, okay? It's gonna go through 10 half-lives in a jiffy, okay? Don't handle that without PPE or you dead, like you literally dead, okay? You have denatured all the DNA and proteins. You have totally screwed up your body. Okay, but if it's short, you just do the math and then you solve for the half-life in the trendline equation and boom, you have it. Okay. So like it looks spooky, mystical. Actually, like at the end of the day, as with many jobs, you have math and or software that can help you figure out stuff like pretty quickly. You're like, I didn't expect that to be that easy to find, but it was. Yeah. Yeah. Okay. Great question. That was awesome. So yeah, there you go, age of the earth and stuff. So that's gonna be the theme of today, is gonna be correcting instability. All right. So let's get started. Okay. We're going to do some nuclear reactions. And you're gonna see there's a bunch of nuclear reactions here. You're gonna be intimidated, like, oh man, I got so many to remember. Okay. It's remember-ish, folks. It's remember-ish. Okay. Nuclear chemistry is really just math. We're just doing math today. Okay. And it's just arithmetic. Like once you do the first few nuclear reactions, you're like, really? That's all I had to do? It can't be that easy. I want you to have that it can't be that easy moment. Okay. Look. You can't create or destroy matter unless you're in a nuclear reactor. Well, we're kind of in a nuclear reactor now. But this is what I would call soft nuclear conditions. Hard nuclear conditions, you are talking about like supernovas and, black holes and like these really like intense energies. Okay. What we're talking about today, we're just starting to transform nuclei a little bit, but we're not turning everything into quark gluon plasma. Quark gluon plasma is when you're at like 100 trillion Kelvin, and at that point, your atoms don't even exist anymore because the protons and neutrons and electrons are all just a soup. In fact, you don't even have protons and neutrons anymore. They've dissociated into up and down quarks. Okay. And you don't even have protons and neutrons anymore. That's when you have a free range of making a whole freaking periodic table. Okay. But that's not where we're at today. So basically, today, it's soft nuclear conditions. Your mass number is basically going to stay the same. Your proton number, not basically, it will stay the same. Your mass will basically stay the same. Your protons will basically stay the same. So what I wrote at the top here is sum of A before reaction is going to be sum of all A after reaction. Just make sure your A numbers are equal on both sides. Okay. An arrow is just like an equal sign, right? And the same with your Z. Okay, all your protons at the start got to be equal to all your protons at the end, or positive charge. Okay, so let's do a little review. This I didn't necessarily put room for on this sheet, but I'm guessing a lot of people want this review. So this goes way back to like week 2 or 3 when we're talking about isotopes. Remember isotopes? We had like this sort of symbol. Yeah, this is the theme of today. Okay, A is called your mass number. And that's equal to your proton number and your neutron number. Man, it's toasty in here. All right. Hope y'all work deodorant. All right. Okay, they're pretty quiet up there. All right. All right. And then the most common mistake is people put the neutrons there. No, there's no space for neutrons. Okay. N is your number of neutrons and Z is your number of protons. We don't really care about electrons here. Okay. We will lose mass today, technically speaking. We will lose or gain mass. Okay. Fusion reactions, okay. You will gain mass a little bit if you're fusing most nuclides up until about iron. Okay. Iron, cobalt, nickel, those are actually your most stable nuclei. Okay, iron, cobalt, nickel, those are most stable nuclei. Everything after nickel, fission is going to be a better outcome. Okay. And so you'll get these little mass differences. This is where you release tons of energy in these exothermic nuclear processes, and lost energy is actually lost mass. Okay, but we're talking about 1% to 2% differences in masses. So when it comes to mass numbers, they're still unchanged. Okay. All right. So here's going to be our little cheat sheet for today for keeping track of all the symbols. All right. Symbols. Number one symbol, alpha. Okay. I call it the ABCs of nuclear chemistry. Alpha, beta, gamma is ABC in Greek. What is an alpha? It is a helium particle. Okay. Alpha is helium. A helium-4 to be exact. Helium-4 is a very stable nucleus. So kind of like how water forms a lot in nature. Okay, water is a very stable product in many chemical reactions. And many nuclear reactions, helium is a very stable product. It's like the water of the nuclear world. Okay. All right, let's talk beta. Okay. Let's pause here just to make sure we're on the same page. So this helium, how many neutrons it got? 2. Mass of 4, but it's got 2. 4 minus 2. Yeah. Okay. All right. Often you'll never even have to care about neutrons. There's a dirty little secret. Okay. All right, so let's talk beta. Beta is a fancy term for a high energy, that means very fastly moving electron. Okay, it's moving at very high speed. So that gets a special name of beta. All right, so what's the charge on an electron, y'all? -1. Oh, that's weird. You got to give it an atomic number of a -1. But it's the opposite of a proton, so that's like the only logical thing you could do. And electrons basically have no mass. Yeah, it has a tiny bit, but give it a 0. Okay. And then there's gamma. Gamma's the easiest, which is why you're not going to get too many questions on it. Sorry. Okay. Gamma, what's a photon actually? And photons, all of light, have no mass and no charge. So it's 0, 0. So Josh, with gamma, does that mean your nucleus doesn't change because there's no mass change? That's correct. Essentially. Okay. All right. Now we're gonna send an electron backwards through time. Josh, that doesn't make sense. This is called a positron. Positron is antimatter. In every nuclear reaction, you create an antimatter particle and a regular matter particle. And this weird world of physics, their mathematical interpretation is that you could argue that a positron is a normal electron that's found a way to travel backwards in time. I don't know how to make sense of that either. Okay. How are you going backwards in time when you're going forwards in time? Okay. There's some reasons why chemistry makes more sense to me than physics. Okay. But whatever, it's going backwards in time. And if you're going backwards in time, you have the opposite charge, whatever that means. Okay. But it does have a positive charge. Okay. And before you're like, Josh, this is voodoo, fake crap science, you're making crap up. Positrons are used in the medical world right now for saving people's lives. Okay. Positrons do exist. Okay. I'll talk about that. Okay. Who's sort of PET imaging, positron emission tomography. Okay. It's a way of detecting, doing imaging in the body. Okay, you might have to learn about that one. Okay. All right. So, all right, we did alpha, beta, gamma. We did the other beta, okay, positron. Normal beta is just an electron. If you just say beta, we're referring to that one. Beta positive is positron. All right. What about proton? We'll have to talk about proton capture a little bit. A proton has a mass of 1 and it has a charge of 1. So there's your proton. Okay. And what about neutron? Okay. This one's going to feel funny also. A neutron has a mass of 1 but has no charge. So right here, this is the hardest part of everything we're talking about today. If you master these symbols, you can do any reaction. You don't even have to memorize too much. I mean, memorize a little bit, but you don't have to over memorize because at the end of the day, you're just going to make the math work out. And this is going to be your toolkit, these symbols for making the math work out. Okay. All right. Yeah, we did them all. Okay. And now we are ready to do nuclear reactions. All right, pausing here. I'll get some tea. Okay. I love this stuff. All right. So before we do the reactions, let's create a little quick cheat sheet. Okay. One of the things I tell people when doing nuclear chemistry is write out the symbols if you need to, and then write out this little square of 4, or 4 square. Okay, not like the playground 4 square, but like this. Okay, what I'm trying to do here is represent the periodic table like 4 tiles in a row. All right. Now in the alpha reaction, you're going to lose 2 protons as a result. So we're talking about a movement from there to there. Okay, so this is your parent. If you have a parent of A, oh my gosh, strike 2. AZX, like that. Then when you go from there to there, you're going to have an A minus 4 and a Z minus 2. And some new X. I'll call it D for daughter. Okay. The new nuclide is always called a daughter product. There are no son products. Okay. Maybe there's some family drama in whoever was coming up with these terms. Okay. But whoever came up with these terms, like their daughters more than their sons or something like that. Some lame joke. Okay. All right. A minus 4 is Z minus 2.
So do we always assume that it's A minus 4? Mass, like the difference in neutrons might be different than 2.
Oh, no, it will. You are losing exactly 2 protons and 2 neutrons exactly.
Okay.
That little mass defect I was talking about how if your nucleus becomes more stable, you're gaining mass energy from E equals mc squared. And if you're becoming less stable, you're losing mass energy from E equals mc squared. But we're not worrying about that.
Okay.
Yeah, it's just a 1-2% mass difference. Okay.
Yeah.
So we're not going to worry about that. The counting of protons and neutrons stays the same. So I'm glad you asked that. You're losing exactly 2 protons, exactly 2 neutrons. Okay. For a total of 4 things. All right. And so that's your alpha decay. Okay. Let's go the other direction. There's beta decay. Okay. Beta decay, you are gaining an electron. The only way you can gain an electron is if you destroy a neutron. Okay. That's gonna feel funky. Check this out. Here's a side note. How does beta decay work? Okay. You normally don't write this as a reaction, but behind the scene in a beta decay, you're like, man, I need more protons. I need more electrons. I got too many neutrons. So this is funky. This is cool. A neutron in nucleus is turned into a proton, and you shoot out an electron in the process, and that's your beta particle. Okay. Yeah, the nucleus goes, hey, I need more protons. I'm gonna kill one of these neutrons, turn into a proton. That's exactly what happened. Okay.
So
Yeah.
a neutron is just a proton and an electron?
Yes. From some point of view, yes. Okay. So you play with a weak nuclear force. The weak nuclear force is what governs the identity of all the subatomic particles. Okay. So you play with a weak nuclear force, you transform a neutron into a proton and an electron. Okay. Notice the charge is the same on both sides. 0 plus 1 plus minus 1 is 0. You can't create or destroy charge in this world. You can't. Or said another way, if you create positive charge, you're also creating negative charge. Okay. There's also something else created called an anti-neutrino, but you don't even know about that. A neutrino has like 1 billionth, I don't remember the number, the mass of an electron. To detect neutrinos, they build these underground labs. Like there's one in Minnesota, man. It's like, it's this huge vat of oil, like the size of like Evergreen building or something. I don't know. And then, you know, you just you have like, you know, the oil has like some phosphorescent property or something. And so like in that one in Google probability event a neutrino hits, you see like a little tiniest light or whatever. And it's like in the darkest like cave in Minnesota or whatever. That's how they try to detect neutrinos. Okay. Oh, yeah. So beta, okay. You're going to end up with a new nucleus. The A stays the same, but you have an X plus 1. And that's why we're going to the right in the periodic table, because you have gained a proton. But if a neutron became a proton, your mass doesn't change effectively. Not much, not significantly. All right, and then this last one, this is the weird stuff. Okay. If you have a positron decay, that means you had too many. I'll put it back. That means you had too many protons. So if you have a positron decay, your proton is going to turn into a neutron, and then that positive charge is ejected on the positron. That's what's going on behind the scenes. Okay. Again, an exam question, you're never asked to write these, but it's helpful to kind of have a sense of what's going on behind the scenes. All right. So the end result is you're gonna have an A, but a Z minus 1. Did I write X minus 1? Oh, I can't even symbols anymore. That'll be your daughter. Go one to the left. Okay. This is gonna happen for positron decay. It's also gonna happen for electron capture, which I'll talk about later.
Can you go back to the positron?
Yeah.
Okay.
T plus gives you N plus a beta with a plus 1 at the bottom left and a 0 at the top left. Okay. And we'll talk about what happens to the positron later. It's a fun story. Okay.
So are there neutrinos made of positron?
Oh, yeah. And you have a regular neutrino made. And it's called an electron neutrino, if you're curious. If you're creating a tau particle instead, it's a tau neutrino. It gets particle physics is so insane. All right. Yeah, you can have supermassive electrons that are not electrons anymore. They're called tau. Okay. It's so insane. So, all right, let's start with an alpha decay. Let's do uranium-238. So you get a nuclear reaction. After all this talk, really all you're going to be asked to do is to fill out a bunch of squares. I kind of ran out of room here. So that plus that. We're going to have two products. Let's do the easy product first. If it's alpha decay, you're going to make an alpha. So tell me again, what was that symbol for alpha? It was a helium, right? And then a 2 and a 4. Helium and 2 and a 4. Okay. All right. So then, now it's just arithmetic time. Don't fight it. Just do the arithmetic. Don't be thinking about neutrons and stuff. The mass number does the neutron crap for you. This is what I mean. 238 minus 4 is 234. Yeah. Just put in 234. That's the answer. I'll write bigger on the next one, but that's 234 for the alpha decay. And how about this other one? 92 minus 2. 90, yeah. Don't fight it. Just do the math. Okay. All right. So yeah, exactly. Your eyes shift to the pure activity. But well, the one with 90 protons is the Chris Hemsworth element. Okay. Thorium. Right. So we make some thorium 234 here. Most of the helium on Earth comes from this very reaction. Okay.
It's always helium in alpha decay?
Always.
Always.
Always. Always helium.
So we determine what the element is by the bottom number, not, because like I wouldn't know. if it
Yeah,
was
it's
like
gotta be the bottom number. This just is a number of protons plus neutrons. This is a mass number. It's, I don't want to call it useless, but it's way less important compared to the bottom left. Yeah. Yeah, the bottom left is the element number. That's your atomic number, your yeah, atomic number. That's what it's called. That's your Z. Okay. Yeah, it's just arithmetic, y'all. Yeah, we can do another one. We can do another one. This one's fun. I don't have room for this on that little sheet I made. Yeah, this is still alpha. And my little hint here is I'm being funny. I'm being funny. This is alpha decay. I'm being funny. This reaction is real though. This happens in star formations. Oh, my bad. I'm off the screen. I'm gonna see if y'all find the humor. Josh, I kind of got 2 alpha particles. That feels weird. You know, that's correct. Okay. What happens as stars are forming and all that stuff, burning their fuel? Okay, you have the heliums smash into each other. It makes a beryllium 8. It hates it so much it goes right back into being 2 heliums. Okay. So that's a double alpha, and that there's other nuclides that will release 2 alphas at the same time, but it's not very common. Okay.
So if it doesn't go to beryllium, then what does it go to eventually?
Oh, it'll smash into like hydrogens, and then helium plus hydrogen gives you lithium, right? And then lithiums will smash, and then you'll basically, to make beryllium, you need an extra neutron. So in your quark-gluon plasma or in your star, you need a neutron from somewhere. It smashes into it, and then you go from beryllium 8 to beryllium 9. And in fact, since you asked, we'll just do the neutron capture right here. Okay. I guess we're over here already, since you asked. Add some other neutron example, but this one's fun. So the hardest part of this is to think of, what the heck is a neutron? Okay. And you hope and pray they tell you the symbol of the neutron, but if they didn't, you'll have to come up with it on your own. So you gotta logic your way through it. It's got no charge and it has a mass of 1. And then you just do the arithmetic, where it's like 9, 4, beryllium. And now this beryllium's happy and it's stable. Okay. And it's ready to go unless something else smashes into it, like another hydrogen, and then it become like a boron. But if a hydrogen doesn't smash to it, it just stays at a 9,4 beryllium. And that is an isotope we find on Earth.
So that's when like fission is going on. But not-
Fusions.
But not fusion.
Yeah, fusions. Yeah, so fusions, basically up until iron, cobalt, nickel. And when you have stars and supernovas and whatever, you're getting up into those three elements, okay? And you have an extra high abundance of iron, especially because it's the most stable of those three, okay? So there's like a stability for the periodic table. It goes iron, and then it goes for all the other elements, okay? That's why we have an especially high number of iron. But basically, up until iron, fusion is favorable. And then when you go past iron, fission is favorable. So when they talk about fusion reactions, not just what happens in the stars or the sun, but they're talking about like having a fusion reactor for Earth. They're smashing hydrogens into each other. And because they're lightweight nuclei, they'll give you energy. But something like uranium, see how far past it is iron. You're not going to get energy from uranium by trying to make it bigger. No, you need to break that sucker to release energy.
So
Basically, you want, if given enough time and energy, the whole world will end up being iron, more or less.
So if like take for instance, when you get closer to iron and you're doing fusion, do they release more or less energy than hydrogen?
Yeah, if you're trying to do fusion on iron, you're not going to get too much bang for your buck. In fact, a lot of the things past iron, you'd have to put in energy to make a new element. That's why you have less of the heavier elements, because it needed a lot of energy to make it stick the landing, but it's not like favorable. Yeah. But it almost begs the question, how come it doesn't go back to being iron? That's because it exited the reaction. It just, the matter got removed from the heat source. And at that point, it didn't have the energy to revert.
Okay.
Yeah. Yeah, but like, yeah, this is where like geology, astronomy, chemistry, physics are all like, this is why I love nuclear physics so much. So, all right, I'm still okay on time. All right. Yeah, this is one of those things, in a good semester, I have 2 days to do this, not just one. All right, let's do a beta. All right, what's my beta example? Oh, I got some strontium 90. Okay, and strontium is 38. Do remember that they don't have to give you that atomic number. You can just look it up based off of the symbol, right? All right, so let's make some boxes. And the hard part is always coming up with the symbol. So if they tell you beta, you gotta be like, all right, what's the symbol? You gotta put a -1. Okay. So now we just do the math. Are we in agreement that the mass number just stays 90? Are we in agreement that our proton number had to go up to 39?
No.
Yeah, because 39 minus 1 is 38. We created a proton by destroying a neutron. Yeah. So let me put it this way, Gavin. If you had destroyed the neutron and it went poof, that 90 should become an 89, right?
Yeah.
But let's remember, we didn't destroy a neutron, we just changed it to a proton. So this is what happened. Like you have 38, at the moment, you have 38 protons, and then you have 52 neutrons. After the reaction, boom, we went up to 39, and then we went down to 57.
Okay.
It went down. I don't know if we got the number right, but the two numbers still add up to 90. So that's why it's good to know what's going on behind the scenes, but this is what I mean by don't fight the math, because it works out. Okay, I'll really write it down.
So-
Fine. Okay. So we got strontium 90. 38. So like if it was like a chapter 2 sort of question, you're like, all right, it's got 38 protons and it's got like 52 neutrons. And then once it did its transformation, what did it go 39? So that's gonna be yttrium. I think that's our first yttrium the whole third semester. All right, so you'd be like this is a 39 and then that's a 51. Okay, so you lost a neutron, you gain a proton, but it still adds up to 90. So that's what I mean by don't fight the math. And now you can see why people like A more than N, because it's lazy, it's a winner for laziness. You don't have to fight the math. Okay, yes.
So a beta reaction is kind of like a reverse neutron capture. It's like a neutron release, but then you like.
It's like a neutron, it's kind of like a neutron release, but you didn't release a neutron, you transformed it. If you had released a neutron, you would have lost a mass number. Yeah. Gavin.
I'm still confused. I think I just wasn't paying attention. So I'm just confused why the -1 is not, because you're talking about the math and it's then it just randomly bumps up 2 or bumps up 1. Why is it adding instead of, even though it's a negative? Or am I like, wait,
No.
because you're saying it's a 39.
Let's start from first principles. Are we in agreement that the bottom left represents the charge, basically?
Yeah.
Okay, and if a proton is a 1 and a electron has the opposite charge, then our only conclusion is it has to be a -1.
Yeah.
Yeah, okay. And from a math point of view, you get that this has to be a 39 to make it 38. From a math point of view, you're feeling it.
Oh, okay, I see
Yeah.
what, okay,
Oh,
okay,
sweet.
so,
Okay.
okay, so it's like,
Yeah.
it's like,
39 plus a -1 is 38.
oh,
I just
okay.
need the numbers to be
It's like
equal.
switched or, okay.
Yeah. This is what I mean by don't fight the math. It's like, that is the hardest part of this chapter is you want to fight the math, but the math works out. You're like, it can't be that easy, but it is. Okay, it is.
Mm.
Yeah. But a neutron turned into a proton. That's why the number went up for that.
Okay.
Yeah.
I just wasn't looking.
No, you're good, man. And my marker is too thick. All right, so gamma, this will be fast because it's kind of like a duh one. All right. Technetium 99 to 43, and at the end of it, you'll have a technetium 9943. It just released a gamma. Okay. You're like, well, what's the difference? There is no difference. Why do we learn it? Well, because it exists. I mean, gamma rays will kill you, so not high enough dosage. But a very, very low dosage, it's diagnostic, right? So, in medicine with radioactive isotopes, technetium 99 is a very common one. You get something called a molybdenum cow, as nothing to do with agriculture, but you milk it for its technetium. And when the molybdenum decays to technetium, you put a little M next to that 99. That means metastable. Okay. So here's my analogy. How it's same yet different, different yet same. In the light lab, we stuck our wire loops into the flame and we excited the electrons. Okay. And then once the electrons were excited, they relaxed back down and released light in the process. Gamma is the same exact thing, except instead of electrons being pushed away from the nucleus, we have protons or neutrons. It's not exactly a push, but we shifted it in the nucleus. Okay. Basically, something like molybdenum that shoots out a technetium, it comes out funky. And the way it comes out, it's not optimal, and then it self-corrects itself, and that extra energy released when it self-corrects is the gamma ray. Okay. All right, so someone eats a little bit of technetium 99, they get an injection. Wherever it went to in the body, you see the gamma rays being shot off, and then you have the detector or whatever, and then it's used for imaging. Okay. All right. All right, let's do positron. This one is fun. Okay. This is also important in nuclear medicine. We're gonna have fluorine 18. Fluorine's a 9. And we're going to make a positron. So it's the weird positively charged electron. So it's going to be a +1 or just a 1. You don't have to put the plus. at the bottom left. It'll be an A, you got it, man, okay? And then an 18 at the top, right? And then you go to the periodic table, you're like, oh, 8's oxygen. That's positron emission.
And so it's the oxygen with a higher mass.
It's an oxygen with a higher mass. And this is actually stable. Oxygen 16, 17, 18 are all stable. Okay. But oxygen 18 is only like 0.001% of all oxygen or something like that. All right. Now, the reaction, the reason this reaction is important in nuclear medicine is fluorine. You can substitute it for oxygen and glucose, and then you can diagnose cancer. Okay. Cancer cells consume way more glucose compared to normal cells. And so if you have a glucose that's labeled with fluorine 18, the cancer cells will take it up in a higher amount, and wherever the cancer is, it'll undergo this nuclear decay, and then that is detectable. The detection is not of the positron, it's of something called annihilation. This is not ever going to be on an exam, but my last information lecture, you gotta humor me, okay? What happens when a positron runs into a normal electron?
It like eliminates, so
What's that?
it just goes away.
Correct. You get 2 gamma rays.
So gamma ray is an electron.
No, the electrons die. When you create a positron, when it finds its matter, when antimatter finds its matter equivalent, there's some sort of physics symmetry principle, something, I don't know. But what happens is when they find each other, they annihilate. And all the mass is converted into pure energy in the form of photons. You have that E equals mc squared. You have the mass of 2 protons put in, multiply the speed of light squared, and you get that energy. And that energy in the photon used to be the mass of the electrons. It gets better. You create 2 gamma rays. They're each 511 kilo electron volts, and they're created at a perfect 180-degree angle from each other. So if you're in a detector, one of the gamma rays will hit the detector before the other, and based off of that, you can do the math to figure out where it was. Okay, and that is how positron PET imaging, okay? God forbid that anyone needs this. I hope not, but there's some freaking cool science there. Yeah,
So like, could you create like anti like elements basically?
yes.
So,
Yes,
like,
there's anti-hydrogen, there's, yeah, you can go nuts, so.
like what would be the purpose of like other than like we just did it? Like
Could you use it? to
Most of
isolate?
science is we just did it, and then 50, 100 years later, oh, we have a use for this, we have a use for this. I don't know the use for it yet.
Can you use it to isolate elements that are hard to isolate or something like that?
I don't, maybe, I don't know, like, but you know, you make the tools, sometimes you make the tools before you know what they're useful for, but yes, you can make anti-elements, yeah. You can make an anti-hydrogen has a nucleus with a -1 charge and an electron with a +1 charge. Again, not practical for most people in here, but if you're into particle physics, you live and breathe that stuff. All right, neutron capture, we did that already. Here, just keep an eye on the clock. Let's do an electron capture next. Okay, I wrote my example down somewhere. And oh, no, I got it. Okay. All right, I'll do the first electron capture example for you. if they ask the electron capture, you just go down an element and that's it, okay? So when we did our cheat sheet earlier, we talked about how alpha goes 2 elements to the left, electron capture and positron goes 1 element to the left, and then beta goes 1 element to the right. So what is the physics in an electron capture? Well, you're capturing an electron. And if you think about it, the only way you can capture an electron is with something capable of catching it. And that is a positive charge, okay? So electron capture, the electron and the proton combine to make a neutron.
So an electron capture is the reverse of beta.
And an anti-neutrino. But what's that?
So an electron capture is the reverse of beta.
It is the reverse of beta. And positron and electron capture have the same outcome. They have the same outcome. Like if I wrote here, oh, do positron, you would end up with a 12 magnesium as well. You would just have a positron on the side. But an electron capture, you get the same nuclide outcome, but it's cleaner because it's all done internally.
Okay.
Yeah. But the mass number stays the same, 26 versus 26, because your proton became a neutron. Yeah. Why? When does an element choose positron versus electron capture? I don't remember all the physics, if I'm being honest. Some isotopes are actually capable of doing either. Okay. But they're two distinct mechanisms. I had another example on me. This one's weird, so I wanted one more example. Oh, there it is. Let's do one more electron capture. Well, hopefully, like, even though we have all these reactions, like, you're getting the gist of like how it's just arithmetic, and you just figure, you know, you just follow whatever name they're telling you, and then you just do the math. All right, so let's do. I tell you, this is electron captured. What happens? Okay, capture the electron, destroy a proton. We're gonna go down to 22, keep the 48, and 22 is titanium. Okay. For any history buffs, okay, if you watch the Oppenheimer movie, Luis Alvarez is the one that discovered electron capture, and this was the reaction where he discovered it. All right. Let's see. We're not putting my proton capture. We didn't do a proton capture, right? No. But proton capture, basically same thing. Let's just let's do some more interesting stuff. All right, let's do a fusion. Yeah, let's do a fusion. Right? This is how our sun is working right now. This is one of the reactions that gets it going. In the sun and basically any star. Not all fusions are clean though. What I mean by not clean is sometimes in fusions or even fissions, you get some neutrons that didn't quite fit. Okay, it's kind of like smashing, you know, two Lego sculptures together, and you got it to click, but like some bricks fell out in the process. It's kind of like that, you know. You can think of the reverse. You break your Legos apart. A few fell out. Those are your neutrons. So then we'd be like, okay, well, they told us it's a helium, so it's a 2. And then, well, it has to be a 4 there because it has to add up to 5, right? So again, no matter what they throw at you, you just do the math, okay? You just do the math. All right, and then fission. Okay, this is how our nuclear reactors work. Most of our nuclear energy, there's a little bit of plutonium, others of the energy, but 90%-ish comes from uranium-235.
Oh, 92.
92, yeah, 92. And then that's a 141. All right, last one, I threw a little curveball in terms of what they're asking for. I wanted to calculate how many neutrons fall out once the uranium-236 crumbles to pieces.
Is the uranium in the beginning, is that 235?
Yeah, 235, thank you, my bad. The uranium has two main isotopes, 238 is the main one, and 235 is the minor one. But 235 is way more important. That's the one that gives you nuclear power. All right, so neutron is a 01, krypton's a 36, barium's a 50 something, 56. We only get neutrons left. So we got to figure out how many neutrons. Mass number 92. Oh, that's a bad coincidence, ain't it? That feels like the uranium number, but it ain't. 92 plus 141 is 233. Okay. So that means how many neutrons fell out? Okay. We have 92 plus 141. Okay, let's do that side math. We have 233 so far, but we had 236 in the intermediate product. So that means 3 neutrons fell out. Okay. And this is where you get those so-called nuclear chain reactions. You have to initiate it from a neutron source. But once you hit it with a neutron, it's self-sustaining until you spend your fuel because it keeps making more neutrons for more reactions. Okay. And you're like, oh, it's too many neutrons. Then you could do a neutron capture. And so you visit INL or whatever, they talk about their boron rods and stuff. So here's how a boron rod works. Boron has what's called a great nuclear cross section. It absorbs neutrons very well. Okay. A good target for neutrons. Okay. When they talk about how well something interacts with nuclear particles, they measure the cross-sectional area in a humorous unit known as barns. Okay, like trying to hit the side of a barn was a joke. Okay, that's why in that printout earlier, you saw a picture of a barn. That was for going to the website, measuring nuclear cross-sectional area. Now, those are like, in femtometers, not in like square meters or anything. But yeah, your boron rod, to slow down your nuclear reactions, you just absorb neutrons, and that way you can slow it down and not have it run away. Okay. In the nuclear disasters, such as Japan, the electronics shut down. Irony, right? When you're a power plant, the electronics had no power, so couldn't control the boron rods to slow down a reaction, and then the fuel cycle overheated and mess. Okay. And then you release strontium-90 into the environment. Everything's related. Last thought before I send you off is half-life. Okay? Half-life, the quick trick is to just divide by 2. Okay. So you could get a question of, something has t½ of 7 years. How long for 6.25% material remaining? This is a classic question. I can almost guarantee this will be on your final. Okay, something like this. It doesn't even matter. They can make it up. Okay. It could be keganium. Keganium has a half-life of 7 years. How long does it take for you to have 6.25% remaining material? Okay. So you divide by 2 in a calculator. Okay. Or you build a table. But you're not going to have a fancy table like that. So you're going to go like this. 100. You're going to divide by 2 one time. First time, you have 50% left. Do it a second time, third time, fourth time. Oh, that's a number. So we had 4 half-lives.
Oh.
Yeah, it's like the penny, but don't select the 4 though. It's 4 times 7 years. So that'd be 28 years. That's how you do that. Okay. They're probably not going to go deeper than 4 because then you get some really weird numbers that we're not comfortable with. They usually ask like 2 or 3 half-lives. It's pretty typical. But that's how you do those half-life questions. No exponential functions required. Okay.
Did we cover proton capture?
No, I didn't do a proton capture. I am out of time. If you have to go, great. I'll see you on Friday. Otherwise, let me hook you up with a proton example. A proton example.
It's just +1 on both. Right?
Yeah, exactly. Let's do. The proton stuff.
So it's supposed to be oxygen.
Correct. Oxygen 15. That's it, folks.
So why is only half is uranium?
Oh, that's because I selected it in the program and then I hit print screen.
That's what
Yeah,
I figured.
yeah. That's like an interactive page. It's not like an actual printout.
And then why is there this big gap right?
That is some crazy physics right there. I don't know the exact reasons of why, but for whatever reason, in that area, you cannot find an optimal combination of anything to keep it stable to save its life. The technical answer is the nuclear binding energy is low. why is it low? Can we get a nucleus and look at the repulsions and stuff going on? That's beyond my pay grade, but that's basically what's going on, is the nuclei for whatever reason, just suck at being stable. And so that's where beyond it, you hear that term island of stability. You can see like that's why like the uranium and thorium is like its mini island of stability. Okay. Yeah, but I don't know why. I may have known it at one point, but I've forgotten a lot. Thank you, you too.
When's the exam for?
It's open right now through Thursday,
Tomorrow.
but today's what, yeah. Hey, if you need that day or two, I can get with you. Just, I figured Thursday was like a good day for most, just to give them some amount of spacing.